All right. 2.2, deductive reasoning and proofs. To recap on 2.1, we've got conditional statements, which are if P then Q. The converse, we switch their place. Q then P. Contrapositive is both a converse and an inverse. If not Q, then not P. And the inverse, if not P, then not Q. Simply negating both statements. For a little review, law of syllogism. If the conditional statement, if P then Q, and if Q then R are true, then if P then Q is true. We talked about the DirecTV commercial. If you have cable, then you throw your remote. If you throw your remote, people think you have anger problems. If people think you have anger problems, they leave you. And if they leave you, then you get cats. And if you get cats, then you become a hoarder or whatever. And then at the very end of the commercial, they say, get rid of cable, or don't hoard cats, get rid of cable. And that's kind of, they're using syllogism with false premises. We have to make sure that we get them all in order correctly. So if A then B, if B then C, if C then D, if D then E. We got to make sure they go in the right order. For example, here we see we've got 4 different statements, but they're not in the right order. But we have to look at A. If we're visited by aliens, then we might panic. Do I see something that talks about we might panic in the beginning? Hint C. If we panic, then we might run away screaming. So I know those two go next to each other. And then we look at the next one. We look at runaway screaming. Do I see anything that says runaway screaming? No. So it can't be that. That means it's got to be the end. So we look at the beginning. If we're visited by aliens, do we see anything at the end? Look at that. We might be visited by aliens. Goes right there. And then we talk about we see a UFO. We see a UFO. We put them in order. The correct order for this syllogism is DBAC. These help you with problems 9, 10, and 11. All right, inductive reasoning uses patterns to make conclusions. Deductive reasoning uses facts, definitions, and theorems to prove their logical arguments, or to write logical arguments. I'm going to get out my notes packet so I can follow along. All right, so deductive reasoning, we're still in the basic concepts area. We're still up at the top. We've gone over deductive and inductive reasoning, and we've talked about the law of syllogism, okay? So just trying to keep you on par with your note packet. All right, so now we're going to do an example about, again, this isn't in your notes. This is just talking about inductive versus deductive reasoning. If Jasmine spent a week in the Pacific Northwest, it rained every day of her vacation, she concluded that it rained every day in the spring in that city. She's using a pattern that she noticed. Okay, so it rains every day. And she's using that to make a conclusion. It rains every day in the spring. Now with deductive reasoning, here we have Hector, who's in the Rockies. He spent a week in the Rockies in the winter. Before he went on vacation, he did research. Notice the word research, facts, definitions, things like that. And learned that the locale, on average, was the temperature of 30 degrees when the skies were devoid of clouds. Devoid meaning without clouds. As the plane descended, he noted that there were no clouds in the sky. He expected, or made the conclusion, that the temperature would be 30 degrees outside and buttoned up his jacket. So he's using research and data in order to predict or draw a conclusion. All right, example 2.9. Here we are in, these are in your notes. These are example 2.9. All right, Jasmine's was inductive. Hector's was deductive. Here we are with Carter. Carter visited New Orleans. This is on the second page of 2.2, example 2.9. Carter visited New Orleans and found the weather was miserable for every day of his vacation. He concluded that it always rains in New Orleans. That's inductive. He's using that pattern of seeing what happens every day. Then we go on Meredith. In all of recorded history, you guys see this right here? In all of recorded history, there were no recorded days where rain did not fall during the season. So she packed an umbrella on the basis of this information. She uses this fact that there was never a chance where it didn't rain. And she used that fact to draw a conclusion. That's deductive reasoning. All right. So question number 1. What is the difference in deductive and inductive reasoning? Inductive uses patterns, deductive uses facts. It's up to you how you want to write your express your understanding of it, but please make it as detailed as possible. Feel free to pause the video right now if you want to take time to write it. Otherwise, we're going to go ahead and move on. So in example 2.10, we're given a statement here. The statement is 4 times x plus 2 equals 3x plus 9. We're asked to prove x equals negative 17. Notice right here, this is the given statement. And down here, this is the prove statement. The first step is given. And to get from step 1 to step 2, what does it look like we did? We used the distributive property to multiply in. And now to get from step 2 to step 3, it appears we subtracted 3x across, which is the subtraction property of equality. Now this last step here, to get from step 3 to step 4, we obviously subtracted 8 across and got the subtraction property of equality. So here we have our statement, and here we have our reasons. The reasons are what we're interested in for this class. All right, proofs. Most examples during this lecture have been in the format of proofs. We're given something, we're asked to prove something, or we have a picture or a diagram, and there's the proof statement. So we're given information, we're given a diagram usually, and we're asked to prove something else. All the examples so far have been done in 2-column proofs. Here we are with elements of proofs, statements. On the left are the statements, and on the right are the reasons. So we've got the different reasons we can give: definitions, postulates, properties, and theorems. On the left, we're going to notice that there's always these statements. But on the right, there's those 4. All right, so there's your reasons. Those are all your options. Here's the elements of the proof from your notes. Same kind of an idea. The basic concept you need to understand is the first statement will always be your given, and the reason will always be given. And the bottom left will always be your conclusion, the thing you want to prove. Okay, we're going to do this step by step, and you'll see kind of some examples. What word will you never be found anywhere in a proof? Think about different thoughts you have or different ideas of words that you'll never find in a proof. All right, so the first one we got to talk about is the linear pair postulate. This is a postulate that describes the measure of angle 1 plus the measure of angle 2 is equal to 180. But the definition of a linear pair is 2 angles form a linear pair. This should say 2 adjacent angles form a linear pair. They are supplementary. So right here we got angle 1 is adjacent to angle 2. That means that they are supplementary because they're a linear pair. And if they're supplementary, then that means that 1 plus 2 equals, angle 1 plus angle 2 equals 180. That's kind of the idea of the linear pair postulate. Right here we've got congruent supplements postulate, or theorem, sorry. Here we have measure of angle 1 plus measure of angle 2 equals 180. That means they're supplementary, okay. Then if measure of angle 2 plus measure of angle 3 also equals 180, then we can skip a step and just say that 1 and 3 are equal to each other. We're cutting out the middleman. We're just saying that we can, if 2 items are supplementary, 3 different angles, and they share a common angle, here number 2, then we can skip out on that and just say that 1 and 3 are congruent. It's a very important part of what you're going to be doing during proofs. Same idea with complements. Measure angle 4 plus angle 5 equals 90, and angle 5 plus angle 6 equals 90. Then angle 4 is congruent to angle 6. Right? We're going to use that in proofs. We're going to use these postulates. Postulates, like I said, are accepted as true. We just think of them as rules. They don't need to be proven. They are what they are. Okay? So theorems must be proven before they are accepted as true. We have to take a couple of postulates, combine them together to create a theorem. And once we come up with a theorem, then we can say that they're answered. We're not going to prove every theorem, but I'd like to be able to do that if I had time. And eventually one day we might be able to get to that point. You cannot use a theorem as a proof itself. On this next example, you can't just say the theorem. You have to take me through it step by step. So right here, given 1 is supplementary to 5, and 3 is supplementary to 5, prove angle 1 is congruent to angle 3. Our first reason is going to be given. Don't ever forget that. The first reason is always given. The next reason, we've gone from the words of supplementary into an equation of some sort. And we use the definition of supplementary angles in order to create this step. We go from 1 to 2 because that's what supplementary means. It means that angle 1 plus angle 5 equals 180. Now this next one, we go from here to here by using the transitive property. Notice how they're both equal to 180. That means they're also equal to themselves. So we say measure of angle 1 plus measure of angle 5 equals the measure of angle 3 plus the measure of angle 5. Now, right here, we're going to say this is reflexive. If something is ever equal to itself, that's the reflexive. Kind of like when you look in a mirror, you see your reflection because you are equal to yourself. 5 is equal to itself. Now, this last step, we're going to combine 3 and 4 to do a little bit of a subtraction property. We're going to subtract the measure of angle 5 from the measure of angle 5 right here. And they're going to go away, and we're left with the measure of angle 1 is equal to measure of angle 3, or angle 1 is congruent to angle 3. And that is how we use this supplementary theorem in practice. Okay. So for this next example, 2.12, we're given an if-then statement. Do you guys see this conditional statement? We've got if the absolute value of x plus 2 equals 5, then x equals 3. Now we've got a couple different options. We know the hypothesis, and we know the conclusion. It's the if and then the then. Is this statement true or false? If it's true, then this is true, and this is true always. But if it's false, then we can find a counterexample, which is true for the first part, but false for the conclusion. So right here, I've got x plus 2 equals 5. Oh, not x plus 2, absolute value of x plus 2 equals 5. Can I think of anything else here that equals a negative 5? Well, I would look at this, I'd say, well, if I set it up like this, I subtract 2 over, and I get negative 7. So I'd say, well, if x equals negative 7, it is true for this side, it does equal 5, but 3 is not negative 7, negative 3. Or negative 3 is not negative 7, and therefore it's false for the conclusion. All right, now don't forget, rewrite the conditional statements and the true converse as a single conditional statement. This is where we get into biconditional statements, and we use them if and only if right here. Okay, so for 2.13, we need to rewrite this as a biconditional. If an angle measures 180 degrees, then it's a straight angle. The converse of that is also true. If it's an angle, a straight angle, then it measures 180 degrees. So we're going to write that as, get rid of the ifs and thens, and we just say an angle measures 180 degrees if and only if it is a straight angle. Or we can use this fancy IFF to stand for if and only if. And we took the red and the blue, which are both true, no matter they go both directions, like a bicycle wheel, front and back. They can go both directions, and therefore they are biconditional, and we write it as if and only if. That might be a good example for you guys to look over for the test. So here's another example, 2.14. Again, it's asking us to take this biconditional statement and turn it into two separate conditional statements. So if I put if there, and then I put a then instead of if and only if, I get this. If two lines are perpendicular, let's see, I get this. Here we go. If two lines are perpendicular, then they intersect to form right angles. That's the first conditional statement. The converse of that, we switch the hypothesis and the conclusion to get right here. If two lines are perpendicular, then they intersect to form right angles. That's a conditional. The converse, if two lines intersect to form right angles, then they are perpendicular. And that is how we get two separate statements. Now here we are at the very end. We can summarize what we learned. You'll see on your notes there's steps for a foldable. We can make that in class one day if we get time. But right now, I want you guys to think about what you learned today. Think about how to use counterexamples to disprove certain things. Talk about the steps in a proof, and hopefully we'll be able to talk more about this in class.